Hi, my name is Jags Ramnaran. I'm the CTO at SnappyData. So SnappyData by definition is a Spark-based open source platform for unified analytics. So one of the primary use cases that you can create what we're calling as virtual warehouses on any cloud. So before I get to describing what SnappyData really is, let's first ask this question we get asked often, which is why does it matter with so many tools in the marketplace already for analytics? So let's start by describing a set of requirements and a set of problems we want to solve, right? So the first thing is that when it comes to analytics, we really want new analytic applications on the cloud with a lot less complexity and a lot less friction than we see today. We also want an architecture that can leverage essentially a lot of the existing assets, especially databases like operational databases that already exist in the enterprise. And a lot of the data, frankly, is stuck in silos. How can you leverage that siloed data, a lot of the emerging data in these emerging sort of operational databases? And we also want to consume new streams of data that potentially is emerging through new applications in the cloud. And finally, we want to make sure that we can offer very high performance for interactive analytics, essentially be able to use a range of applications right from self-service BI tools, microservices, and even real-time dashboards. Now, well, it turns out that cloud analytics is not all that simple. So take this graphic that you see on the right. It essentially depicts, if you may, a typical pipeline for how data is prepared for analytics, where the data is emerging in silos and operational databases. You essentially go through an expensive batch ETL process today, which moves the data from these operational stores into a warehouse. Typically, it's denormalized into cubes so that when it comes to interactive analytics, you get essentially higher performance. Likewise, we also see a range of new applications that are dumping data into these NoSQL-like stores, and from that stores again you are doing ETL to a traditional warehouse, which is even more complex given that the data is no longer flat. Finally, extract the data into files, and then you'll end up pumping the data into cloud storage, say S3, and that's where there's a big challenge, right? Because it so happens that even if you have 100 megabits per second connection, which is sustained, a terabyte of data transfer would take anywhere from 28 to 48 hours, let alone you're not running into, essentially, you have to assume that you won't run into problems. So what we see is folks quite often resort to specialized devices like the AWS Snowball, which you can essentially get to plug it into a network, copy your data into that device, and then ship that device. Or even land up using, for very large data sets, land up using the AWS trucking service, which is, again, all this is very expensive, very intrusive, right? On top of this, what happens if the data that is you've shipped is in fact changing, which is in fact the case if your really data is coming from operation stores, which implies that you have to repeat this process over and over again. What it amounts to is that if you are really trying to get all this data into the cloud, it is rather complex and the cost is rather very high. Now, what happens once the data is in the cloud? Well, it turns out even once it's in the cloud, it is rather very complex. So here is a processing architecture in the cloud, which is it's become a de facto standard. It's called as a Lambda architecture, and it is in fact from the AWS website. It's an example for a news aggregation service. I won't go into all the details, but suffice it to say that the architecture is rather complex. The data is ingested in batch into S3. The real-time data is ingested into some other real-time store, like in this case DynamoDB. And finally, for interactive analytics, the data is emerging through multiple databases: a relational reporting database, Presto for interactive analytics, and of course DynamoDB, which is a key value store. And it is an application that has to now stitch all this data together, let's say doing a join, let's say doing a correlation. All this is very unnecessarily complex. And of course, let alone time consuming, because you really have to master all these products in some sense, right? So what we're really proposing is that we are introducing, essentially, think about it as a layer that sits between your data sources and your cloud analytical applications, right? what we're calling as an in-memory driven virtual warehouse, which you can spin up or spin down on any cloud very easily, and which can dynamically expand or contract, right? It essentially discovers, catalogs, and caches hot data on the cloud local nodes. But the most important thing is that you can essentially federate your queries, your analytical queries, on data that's residing in main memory, data that could be literally be in your in your original data sources itself. In other words, the queries are analyzed and the right portions of the queries are directly shipped to your data stores, and we can do a federated query across your data sources and data that's sitting in main memory. And the primary idea is that for most of the data that you need for analytics, you essentially land up running those queries primarily in main memory, and it is significantly faster. Now, one way to think about this is like a new cloud cache that is purpose built for analytics. Like, for instance, you might be used to Redis or an Elastic cache for highly concurrent, let's say, key-based lookups, transactional applications. But think about Snappy as something equivalent as a caching tier, but is primarily designed for analytics, which basically means your input is ad hoc queries, and your data is very large, and the data comes from many different classes of data sources, right? It primarily runs in main memory, so you often don't have to do all this laborious ETL. You don't have to generate cubes. It's so fast that you can just dump your raw data and run your queries really, really fast. So in some sense, this is kind of what we think about as a virtual warehouse, and it can run, in fact, on any cloud. I would also say that you shouldn't be confusing this to a product like Snowflake, where the data is all on S3, and it isn't really meant to work directly with your operational stores, right? With SnappyData, you can keep your data on S3, you can retain it inside your operational NoSQL, SQL store, or even HDFS, and we would land up dynamically pulling the data into caches, perhaps even one sort of cluster per application if you want. Much easier to get this going. We will show you through a demo, right? So how does it really work? Here is a very, very simple depiction. You start a cluster which essentially launches an in-memory store inside of Spark. We parallelly connect from the cloud to any data source, which could be S3 or of course to your on-prem data sources, and we can draw out the schema. We can infer schemas automatically. We can register that into our catalog, and then we dynamically pull the right data sets into distributed main memory. And of course, we can even retain the data in S3, for instance, that we pulled in. And the most important thing here is that, hey, you can literally retain the data in raw form. Of course, you might be enriching it, but the point here is that you don't have to really generate cubes and aggregations, go through a complex pipeline, use Lambda or even BI extracts, because the data can be served at pretty amazing speeds. And finally, the important point also is that if the data does in fact change in an operation stores, you can rely on change data capture mechanisms, so that as the data changes, they can be pumped directly into the cloud. And we deliver this multi-cloud strategy through Kubernetes. We'll get into it as we demo it. And the applications now interact with SnappyData using a range of APIs. The Spark, Java, Scala APIs. We support SQL through JDBC and ODBC. And of course, you can also use REST to come in and essentially interact with the system. Here's a pretty high-level view into bit more of the architecture. One way to think about how we have implemented this is to look at it as if it's like Spark++. At the shell all looks like Spark. What I mean by that is you land up using Spark SQL. You can use essentially any of the Spark APIs, the streaming, the graph, the MapReduce, the ML APIs in Spark, and then for connectivity to all sorts of data sources, we again rely on Spark connectors, right? And almost every modern data source has made sure that the latest version of the products are all enabled through Spark. And the guts of Spark is where we bring in a lot of the meat, right? We have our own in-memory database that's highly concurrent, provides much significant higher performance. We're introducing essentially the first generation of what's called as approximate query processing. And of course, it's also capable of running transactions.